Hi, so let me walk you through a new project I was working on called arXiv. This is a Langgraph-based agentic RAG system for asking questions about indexed archive papers. Let me explain what was built, why the major choices were made, and where the project boundaries are. So let's get through the architecture first. The main graph is exported from agents.ts file. Langgraph.js.dev is loading that graph through langgraph.json, and Langgraph Studio is providing the conversational interface. I did not build a custom frontend because the Studio already provides a strong UI plus tool call inspection for this kind of agent. The agent has 4 tools: download archive paper tool for fetching and indexing one archive paper, resolve archive paper, which resolves a title, archive ID, and bibliographic hint to an indexed paper. Then query archive paper docs is used to retrieve evidence chunks inside one result paper, and calculator is using a math library for evaluating expressions with a deterministic tool call. Normal question flow is like this. The user asks a question in Langgraph Studio. The model decides if it should answer directly, ask a clarification question, refuse, or call a tool call. For paper-grounded answers, it resolves the paper first. It queries chunks only after it has valid paper ID. It answers from the returned chunks and or refuses when the context is not enough. Batch integration uses post endpoint from /tools/download archive paper endpoint. It exposes a HONO application from app.ts. That route calls the same download archive paper tool the agent can call. For storage, we are using PostgreSQL with pgvector. Papers table is storing archive metadata, abstract text, and 1536 dimensional summary embeddings. Paper documents table is storing chunks, chunk embeddings, and a generated TS vector. H and SW indexes handle cosine vector search and make them fast. A gen index handles PostgreSQL full text lexical search. This gives the 2 levels of retrieval. First, resolve the paper and then only search inside that paper. Now let's get to how the agent is working. Agent.ts is where we are choosing the chat model, the attached tools, and we are exporting the agent that the Langgraph is running. For model setup, the first thing that the file does is to choose a model from the environment variables. If OpenAI proxy-based URL is existing in your .env file, we are using chat OpenAI with GPT 5.4 mini model or GPT 5.5 model, depending on your preferences. If it is not configured, but Google API key exists, then we are using chat Google with Gemini 3.1 Flash Lite preview model or Gemini 2.5 Flash Lite model. If neither path is configured, the file throws error during startup. For Langsmith metadata, the model config includes Langsmith metadata using ls provider or ls model name. This helps Langsmith label traces correctly. Tool setup is coming from index.js file from tools. Right now it consists 4 tools, so the model can use either one of those tools for answering the question. About the agent loop, the actual agent is created with create agent. It is passed the model. We are passing the tools and the system prompt. We are not manually building graph nodes and HS here. Create agent gives us the standard React style loop. The model reads the user message and system prompt. The model decides whether to call a tool. The tool runs and returns an observation. The model reads the observation, and the model can either decide to call another tool or answer the question based on the retrieved context so far. For the prompt comes from prompts.ts file. It tells the agent how to choose between the tools. It should resolve a paper before querying its chunks. It should query paper docs only after it has a valid paper ID. Download only when the user explicitly asks to fetch or index the paper. It should ask for clarification when the paper request is ambiguous. It should use the calculator for math-related question, and it should refuse grounded answer requests when it cannot find relevant papers in the DB. We are exporting the model and the agent. Agent is what the Langgraph Studio is using and on which the graph server runs. The model is also reused by the eval script as the LLM judge model. Up next, for the download archive paper tool, this is the indexing tool. If a paper is not already in our database, this tool fetches it from the archive loader, breaks it into chunks, embeds it, and saves everything in the DB. The important thing to remember is that this tool should not be used for normal question answering. The system prompt explicitly tells the agent to call it only when the user explicitly asks to download, fetch, or index a new paper. It takes the archive ID as a parameter. First, the tool checks the papers table for the same ID. If the paper is already present, it returns skipped existing. That makes the repeated injection safe and avoids creating duplicate chunks. If the paper is not present, it uses LangChain's archive retriever with get full documents true. This gives us the paper metadata along with the full text content. After that, it cleans the null bytes from the title, author, summary, and page content. This is important because null bytes break database rights. Then it builds one summary string from concatenating the title, the authors, and abstract. The summary string is embedded and stored on the papers row as summary embedding. Later, the find paper tool searches against this field. Next, the paper is split into chunks. The splitter lives under the archive shared.ts file and currently uses a 3000 characters with 100 characters of overlap. Each chunk gets its own embeddings, and the tool writes those chunks to paper documents. The paper row and document chunks are written inside one transaction, so if the chunk insert fails, we do not leave behind a half-indexed paper. The embedding uses a local Olama model when embedding models is set to Qwen3 embedding 8 billion model. Otherwise, the code uses Gemini embeddings to model when the Google API key is configured. Next, let's go through the overall agent and Langsmith. The project has one chat agent graph, one small HTTP endpoint, and Langsmith to trace and evaluate the runs. What Langgraph.json is doing is that it exposes two entry points. The graph entry point imports the chat agent. The HTTP entry point imports the Hono app. Studio and Graph API traffic use the graph entry point. Batch ingest is using the HTTP entry point. For runtime paths for chat, Langgraph loads agent from agents.ts file. The user sends a message through the Langgraph Studio or the Langgraph API. The agent chooses the tools as needed. The final assistant message is returned. For batch ingest.sh is reading the archive IDs from the metadata.json. The script posts each ID to /tools/download archive paper endpoint. The HTTP routes invoke the same download tool available to the agent. Paper metadata, summary embeddings, chunks, and chunk embeddings are stored in the DB. For evals, run eval.ts file reads from the eval.json. It runs the real agent shape against those examples. It swaps only the retrieval tool implementation for application runs. It records the runs and judges the feedback in the Langsmith. Langsmith is the observability layer. When tracing environment variables are present, Langsmith records the run. For this project, it will show the user input, model calls, tool outputs, the final response, timing, and metadata. Langgraph Studio is useful for stepping through a single graph run. Langsmith is useful for comparing traces across runs and eval experiments. Token usage comes from model response metadata. The provider usually returns input tokens, output tokens, and total tokens if you're using the API key instead of the proxy. Langsmith can use that usage metadata plus provider model information to show token counts and estimated costs. So how is the find paper tool working? This is just a lookup tool. Once papers are already ingested, this tool helps the agent figure out which paper the user is actually talking about. If the paper is not already in the papers table and this tool cannot find it, it will return not found to the LLM. This step is only about returning a title, archive ID, or short paper description into paper ID. It does not index papers or searches inside the chunks. The input is just taking a query that is not empty. In the prompt, we tell the agent to pass a clean title or archive ID when the user gives one. So if the user says, according to attention is all you need, along with some question, the agent should search for attention is all you need paper, not the entire question. Walkthrough. So the tool is embedding the query first, then it compares that query embedding against papers.summary embedding. That summary embedding was created by the download tool from the paper titles, authors, and abstracts. So this search is paper level search, not chunk level search. The database query ranks rows by cosine similarity and returns the top 3 candidates. Up next, query paper tool. This is a retrieval tool. It expects a specific paper ID. This tool searches inside only one paper. It does not choose between papers. It takes paper ID and retrieves the chunks that are relevant to that relevant question. The input looks like it is taking paper ID, question, and a lexical query. First, the tool embeds the question, then it runs the vector search against paper documents.embeddings, but only for rows with selected paper ID. After that, it optionally runs PostgreSQL full text search against paper documents.page content search. This only happens if the lexical query is not empty. So we have two rankings: semantic ranking from the embeddings, lexical ranking from exact text search. The tool merges those two rankings with reciprocal rank fusion. That gives one combined ranking that can reward chunks found by either search method. Finally, it keeps the top 3 chunks and returns them in order. Currently, the retrieval settings are document vector limit are set to 80. For lexical limit, they are set to 80, and top document chunks are set to 3 with RRF constant set to 60. This tool gives the agent additional context. It does not write the final answer. The final answer still depends on the agent reading these chunks and deciding whether the context is enough or not. If it is not enough, it will call this tool again. Regarding the evals and habilitation, Here we are checking the agent against a fixed set of examples from eval.json. Eval.json is just an agent rubric in data form. Each case has ID, input question, expected behavior, reference answer, and rating notes. Expected behavior can be either answer that agent should is expected to answer. The agent should otherwise the agent should ask clarification questions. Otherwise, the agent should avoid answering directly, which is a refusal case. The cases cover paper Q&A, ambiguous paper names, medical refusal, behavior, and calculator use. Run eval.ts is the script that sends those cases to Langsmith and compares retrieval variants. The script uses the same tools as the real agent. The only thing it swaps is the implementation for the query archive paper docs tool. So each run uses a different retrieval strategy. The script does this. It reads the eval.json file. It connects to Langsmith with new client. It deletes the existing dataset named eval if it exists. This was required to make edits to the evals.json file locally and have them reflect in the database. It recreates the dataset, inserts each JSON case in the Langsmith example. It builds 3 eval agents which differ only in the retrieval method. It runs each agent against the full dataset. It takes the last agent message as the answer. It grades that answer with a LLM judge. It prints the comparison matrix and Langsmith links. The 3 retrieval variants are namespace top K lexical RRF, which is the current production retrieval tool, which is scoped to paper ID with vector retrieval, optional PostgreSQL lexical search, and reciprocal rank fusion. The second one is namespace top K, which is just vector search retrieval scope to the resolved paper ID. And the final one is global top K, which is vector top K retrievals across all indexed document chunks. All of these exports the same LangChain tool with name query archive paper docs. This keeps the agent same and only changes the retrieval techniques. The habilitation tools live in tools/habilitation/query archive paper docs.ts. This file exports only 2 tools: global top K query archive paper docs and namespace top K query archive paper docs. The production tool remains in tools/query archive paper docs.ts. Run eval.ts imports all 3 of these tools and chooses which one to attach to each eval agent run. When it comes to the judge is created using OpenEvals. The prompt tells the judge to return JSON with a score and reasoning. The feedback key is assignment score, so that the score is the name you see in the Langsmith. These are the Langsmith experiments. They run real agent loops, records traces, and then uses another model called to judge if each answer matched the expected behavior. And at the end, the script prints an habilitation comparison matrix by eval case, a summary table with past count, total count, accuracy, and Langsmith URL.